Okay, so now let's take a look at what we could do if instead of trying to estimate a mean from one population, we've got two different populations and we want to estimate what is the difference in the means between these two populations. So we've seen plenty of problems like this in the past. So now we're going to assume that we've got two different independent random variables. That's important here, that these are independent random variables. Where x is from a normal distribution with unknown mean and unknown variance. Y is from a normal distribution with unknown mean and unknown variance. So in order to construct these interval estimates, it's going to be useful to know what the sampling distribution for these things looks like in theory. And so let's assume that we pick from population X a sample size N1, and we pick from population 2 a sample size N2. So what I would like to show is that the expected value for the difference in the means is actually the difference in the two population means. And secondly, what I'd like to show is that if I want to measure the width of the sampling distribution of x bar minus y bar, I can calculate the variance of that distribution. And in fact, it's going to come out to be some combination between variances of the two distinct populations that we have. So for the expected value, this is going to follow something similar that we've done. So I want to calculate the expected value of this difference. Because these are independent, I could split this up to be the expected value of x bar minus the expected value of y bar. And we know what each of those are, but just for the sake of being detailed here, x bar would be the sum of the xi's from 1 up to n1, all divided by n1. And the expected value for y bar would similarly be the sum of all the y's for j going from 1 up to n2. Let me get that subscript n sub 2. And we're going to divide all of that by n2. And so we can pull out the 1 over n, and then we're going to sum n1 times. All of those expected values are the same since they all come from x. And over here, we can pull out the 1 over n2 from inside the expected value. And what's left is n2 times the expected value of y. And these constants, the n1 and the n2's cancel. So what's left is the expected value of x minus the expected value of y. In other words, mu x minus mu y. And so let me just say that we've already seen the expected value of x bar is mu x, and the expected value of y bar is mu sub y. So we could have just said from this stage, well, we've already seen that is mu x, and we've already seen this is mu sub y. Okay, so now let's try and prove this statement about the variances. And so with variance, keep in mind that we're calculating the expected value of something squared. So when I break up the difference here, it's going to be the variance of x bar plus, and when we pull out that constant minus 1 in front of the y bar, we square it. So we actually get minus 1 squared times the variance of y bar. And so the variance of x bar, that's sigma squared x bar. And now the minus 1 squared becomes a positive 1. So that's why we actually add these two as opposed to take the difference. And then from the central limit theorem, we've already seen that the variance for x bar is going to be sigma x over the square root of n1 squared. And the variance for sigma y bar is going to be sigma y over the square root of n2 squared. And so when we square both of those, we get exactly that the variance of the difference of the means is equal to the variance of x over n1 plus the variance of y over n2. So this is going to be a useful property when we want to estimate the standard error for the distribution of the difference in sample means.